Hello guys, welcome on Tesla Adventures. In this video, we are going to discuss the cyclic processes. So first of all, what is a cyclic process? So cyclic process is the process in which gas returns to the initial state from which it has started. So you can see that this gas has started from A, then it goes to B state, and then again it comes back to A. So this is a cyclic process. So let us analyze the types of cycles. So you can see that obviously in cyclic process delta U will be 0, because delta U is the state function, which means that it depends on the fact that what is the state of the gas irrespective of the path through which gas has attained that state, which means that if this gas will go from A to B and then it will again come back to A, then we can say that the initial and the final temperature of the gas will be same, and therefore the delta U will be 0 in this case. So in any cyclic process delta U will be 0, and therefore the work done in cyclic process will be equal to the heat supplied. Okay, so this is a very simple thing. Now let us see the work done. So we know that work done in a cyclic process or in any process is the area under PV graph. So let us see that, let us analyze this cycle first of all. So let us see that if gas moves from point A to point B, then the work done will be the area bounded between this graph and the volume axis, this area. Okay, and this area would be positive because it is expansion process. And when the gas will return back to the original state through this process, this one, then the area bounded between the graph and the volume axis will be this one. So the net area, obviously this work done would be negative because this is compression. So the net work done will be the red area, this complete area, minus this blue area, which is obviously the area bounded inside the cycle, this area. Okay, so this is the work done. So work done in a cyclic process is the area of the cycle, area bounded in the cycle. So work done in cyclic process is area of cycle. Okay, now let us see that now we know that in this case, in the case when this is pressure, this is volume, and cycle is clockwise like that, so you can see that the bigger area is of positive work done, therefore work done in this case will be positive, and therefore Q will be positive because Q is equal to work done. So heat is supplied to the gas and work done is positive. Net heat is supplied to the gas. But in the case of anti-clockwise cycle, in this anti-clockwise cycle, you can see that on the bigger pressure, this graph which is coming from B to A is compression graph, and this compression is occurring at higher pressures, and this expansion is occurring at lower pressures. So the bigger work done would be of compression. Therefore the net work done in anti-clockwise cycle would be negative and Q will be negative. But this is these two things are only valid when the pressure is on y-axis and the volume is on x-axis. And in each question, before answering the question, you have to check that whether pressure is on y or on x-axis, because if we interchange the pressure and volume axis like this, you can see, then obviously you can see in this case that if the gas is going from A to B, then this is expansion which is occurring, and expansion is occurring at higher pressure. So the bigger work done in magnitude would be positive, and the compression is occurring at the lower pressure. So the smaller work done in magnitude will be negative. So in this case, the net work done would be positive when cycle is obviously anti-clockwise, and the heat supplied to the gas, net heat supplied, would be positive. And similarly in this case, you can see that if gas is going from state A to state B, then this is compression because volume is decreasing, and volume is decreasing at bigger pressure. So at bigger pressure, compression is occurring, therefore the bigger work done would be negative, and the smaller work done would be positive. Therefore net work done in this case would be negative, and the heat supplied to the gas would be negative. So this is the cyclic process basics, and let us also see that what is the efficiency of a cyclic process. So efficiency of a cyclic process is the work done by the gas divided by heat supplied into 100 if efficiency is being asked in percentage. But in this case, let us analyze the problem. We know that in this cycle, work done would be the area of the cycle, and area of the cycle will be the area of this rectangle. So this is V0 and this is P0. So the area of the rectangle will be P0 V0. And we know that delta U will be 0 because in cyclic process delta U is 0. So heat will be plus P0 V0. So many of the students answer efficiency as 100% because in all the cases in cyclic process they would be getting same work done and same heat supplied, and therefore they answer the efficiency as 100%. This is absolutely incorrect because obviously this Q is not the heat supplied to the gas. In fact, this is the net heat supplied to the gas, which means that if in this cyclic process I have supplied 6 P0 V0 heat to the gas, for example, I am just taking an example. So if I have supplied 6 P0 V0 heat to the gas and I have released 5 P0 V0 heat, then the net heat would be P0 V0 obviously. But what is the value which we have to keep in this formula is the heat supplied only. So the heat supplied in my example is only 6 P0 V0, not the net heat. So this is the difference. So this is the wrong observation, and therefore let us talk about the correct observation. The work done which we calculated was obviously correct, and now let us analyze each process. So now process BC is a isobaric expansion, and in isobaric expansion you can see that P is constant and volume increases, V increases, and therefore temperature increases. So work done would be positive, and heat supplied dQ will be, in fact du will be positive, and dQ obviously is sum of these two, so it would be positive. So in the process of BC, heat is being supplied to the gas. So let us name this heat as Q1. So Q1 will be NCP dt because this is a isobaric process, and in isobaric process heat supplied is NCP dt. So Q1 will be N. Now it is given that it is a monoatomic gas. Okay, so N is N. Let us use another page. So Q1 will be NCP dt. So Cp is 1 plus F by 2R. And for monoatomic gas, F is equal to 3. So Cp will be equal to 5 by 2R. This is Cp. So Q1 will be N Cp, which is 5 by 2R, and dt will be the temperature of C minus temperature of B. Now temperature of C will be 2 P naught 2 V naught upon Nr, and temperature of B will be 2 P naught V naught upon Nr. So the temperature of C will be 4 P naught V naught upon Nr. It would be 4 P naught V naught upon Nr minus the temperature of B will be 2 P naught V naught upon Nr. So cancelling Nr with Nr, this would be 5 P naught V naught. Okay. So this is the heat supplied in process BC. Now in CD, this is a isochoric process. So CD is a isochoric process, and in isochoric process you can see CD is a isochoric process, and in isochoric process volume remains constant. So if this volume remains constant and pressure is decreasing, then temperature will be decreasing, obviously. P decreases, T decreases, and work done will be 0 because volume is constant, and delta U will be negative because temperature is decreasing. Therefore dq will be negative. So this heat is negative, and obviously this is released by the gas, so we do not have to consider this heat, and we do not need to find out this heat. Now in process DA, you can see that process DA is just the reverse process of BC. So again in DA, heat will be negative because in BC heat was positive. So process DA is a isobaric process in which volume is decreasing, so work done would be negative, and pressure is constant and volume is decreasing, therefore temperature would be decreasing, and therefore delta U will be negative. And therefore if delta U is also negative and work done is also negative, then we can say that the heat supplied will be negative, and we do not have to consider that heat. And in process AB is again isochoric process in which pressure is increasing. So in process AB, now if we directly talk about AB is isochoric process, and volume will be constant in AB, and pressure is increasing, therefore temperature will be increasing. So work done will be 0 and du will be positive. So dq will be du and will be positive, and therefore heat is also being supplied in this process. So Q2 is the heat supplied in this process and will be NCV dt. And obviously temperature at A is P naught V naught by Nr, and temperature at B is 2 P naught V naught by Nr. So we can say that Q2 will be equal to N. Cv is F R by 2, and F for monatomic gas is 3, and dt will be 2 P naught V naught upon Nr minus P naught V naught upon Nr. So 2 P naught V naught upon Nr minus P naught V naught upon Nr. So Q2 will be equal to 3 by 2 P naught V naught. So the total heat supplied to the gas will be equal to Q1 plus Q2, and Q1 was this one 5 P naught V naught, and this is 3 by 2 P naught V naught. So this is 5 P naught V naught plus 3 by 2 P naught V naught. So Q supplied will be equal to 13 by 2 P naught V naught, and work done was P naught V naught. So efficiency in this case will be work done upon heat supplied. So efficiency will be P naught V naught upon 13 P naught V naught by 2, so it would be 2 by 13. Okay, so this is a very important problem for calculating the efficiency of a cyclic process. And what you should remember is the fact that dq in a cyclic process, when dq is the net heat, will always be equal to the dw. So you do not have to consider dq, because dq is the net heat, but we have to consider the heat supplied to the gas. So individually we have to find out the heat supplied, and then we can put the values in this formula. Now let us see the reversible process also. So you can see that a reversible process is a process which, let's suppose, this gas is moving from A to B from this path in which C occurs before D, and then D occurs, and then B occurs. So when gas is moving from A to B, the sequence of states is A, C, D, B in going forward direction. A, C, D, B. Now if this gas is coming back to the initial state A by the same path, and the states which appear in this sequence A, C, D, B reappears in just reverse sequence B, D, C, A, then this complete process is called as reversible process. Or we can also say that this single process A, C, D, B, which can be reversed by this path, is also reversible process. So it is very important to note that reversible process need not to be reversed, but reversible process is the process which can be reversed at any point of time by the same path, and the intermediate states which are occurring in the forward direction in a fixed sequence are reappearing in the reverse direction again in the just reverse sequence. So this is a reversible process, and obviously the delta U in reversible process, in which I am talking about the complete reversible process in which gas moves from A to B and again B to A. I am not talking about the single direction reversible process A, C, D, B. Okay, what I am saying, that this is also a reversible process which can be reversed. So if a gas is moving from A to B and it is moving very slowly, therefore we can say it can be reversed, and process AB is a reversible process. But I am talking about the complete process which is being reversed. So delta U in this process is 0 if gas comes back to the initial state. Work done will be 0 if gas comes back to the initial state, because the path which gas has chosen to go in the forward direction is the same path which gas has chosen to come to the initial state, back to the initial state. So work done will be 0, and therefore heat supplied dq will be 0. And quasi-static processes, we have already discussed the quasi-static processes which are occurring infinitely slow. So those all processes are reversible process. So this was the complete analysis of cyclic and reversible process, and in the next video we'll be bringing some more concepts of thermodynamics. Thank you.